All right, Bismillah. So I continue with the second part of this chapter 7, um, and so we'll talk about again allosterism. And if you talk about allosterism, it turns out there are two standard um, models that are used to explain allosterism, right? So these models are called the considered model and the sequential model. Um, and they're both used to explain what's called allosterism or cooperativity or sigmoidal behavior, right? Now remember, allosterism is the concept that binding of one molecule to one of the subunits of a protein or an enzyme would change the activity um, or the affinity for the other subunits to bind to this molecule of substrate as well, right? And now there are two models, as I said, the considered model and the sequential model, and both of them are actually used to explain allosterism. It turns out some enzymes they appear to be following the considered model, or some proteins, and whereas other proteins or other enzymes, their behavior is better explained by the sequential model. Okay, so what are these models? Let's discuss them one by one. The considered model is also called the Wyman-Monod-Shanguay model. It was proposed in 1965. Again, it's not important to memorize that. There's no need to memorize that. What is important to memorize is that in this model, they're saying that the enzyme or the protein can exist in two conformations, and these conformations are called the R or the T conformation. See, R stands for the relaxed conformation, and T stands for the tight or the taut conformation. So, in the if the protein is in the R conformation, um, this protein can bind substance very tightly, and this is the active form of the protein. So there are two models. There is the R and the T. One of them is the active, one of them, and the other one is the inactive form. So R is the active form, and the T is the inactive form, and T binds the substrates less tightly. So if you don't have a substrate, then of course there is no need the enzyme to be active. So in the absence of substrate, the enzyme exists in the T or the inactive form. When you have the substrate, then the equilibrium shifts from T to the R form or the active form substrate, right? Um, Now in changing from T to R, in the considered model, again, the whole idea is that you have many subunits. So when the enzyme changes from T to R, T again is the inactive, R is the active. So when the enzyme is changing from the inactive to the active form, all subunits, and that's the keyword, all subunits change the conformation simultaneously at the same time, and that's called the considered model, right? And this model assumes the lock and key model of substrate binding. Okay, so again, the considered model, you have the R form, and R is the active, and then you have the inactive, which is a T form, right? And the way I remember active and inactive, we know that R can be made to sound like reactive. Reactive has active and has R in it. So R means active. And of course, then T would be the inactive form. So just make sure you understand what is R, what is the T. R is the active form and T is the inactive form, right? And so there is an equilibrium, right, between R and T. R is the active form and T is the inactive form of the enzyme. And this equilibrium is represented by a constant called R. Sorry, equilibrium constant called L, and L is the ratio of T over R. So if L is big, that means T is big, so you have mostly in the inactive form. If L is small, then you have mostly in the active form. So so high L means most of the enzyme are in the inactive form. Okay. Now what they're saying is, so there is this equilibrium between them, and if you put a substrate, again, substrate will bind to the R form of the enzyme, and it'll actually form this ES complex. And so binding of the substrate will push the equilibrium to go in this direction, and that's why when substrate binds to it, the enzyme changes from T to R conformation because you're going in this direction down. Okay. Um, and of course, in this model, you can have allosteric, activators or inhibitor bind to it. And what they're saying is, so this is the equilibrium, right? So if you have an activator will bind to the R form, to the active form, and stabilize that. So activators bind and stabilize the R form. Likewise, if you have an inhibitor, which is shown here, the inhibitor will bind to the uh, T form and stabilize that, right? So inhibitors go in that direction, stabilize the equilibrium in that direction, and the activator uh, push it in this direction. So the activator stabilize the R form, and the inhibitor stabilize the T or the inactive form. So please make sure you understand that. So an inhibitor will bind to the inactive form, the R will bind to the active form. And as we saw last time, if this is the sigmoidal curve for the enzyme, then inhibitor would push it in that direction, um, and the activator will push in the left side of the graph, and that's shown there. So please take a look at the book. The book explains this a bit more. Don't worry about all these details and all this, but it explains what's happening, but don't memorize all these details. Just make sure you understand how things are happening, and this part is explaining how things work as well. So please take a look at the book and please read this. It should make sense to you guys. Okay. Now, that's called the concerted uh, uh, model. Um, and the other model is called the sequential model. And the sequential model, as the name suggests, is sequential, right? So things happen one at a time, not at the same time. Uh, so in this model, again, you have the T form and the R form. R is the active, T is the inactive form, and again, binding of substrate causes the shift from L to T, T to L, R form. Um, uh, in this, we said this model, the enzyme change uh, is explained by the induced fit model of substrate binding as opposed to the lock and key model. Um, and this model, the sequential model, explains the cooperativity better than the other model, which is the concerted model. Okay, so in the sequential model, um, again we have R, and same thing. R form is favored by the activator. R is the active form, um, and we talk about the induced fit model, right? And then this is again the point is to really see here um, in the sequential model that you have the inactive form, substrate binds to it, and is going to cause it to become the active form, right? It's going to stabilize the active form. Now, when is the way it happens, you find if you look at this is a dimer, you have two subunits and then you have two subunits. What happens is binding of the substrate to this substrate to the active side or to the allosteric side of the enzyme will cause a conformational change will happen, and this conformational change is happens to one subunit. Like now you can see one is R, one is T, and then eventually it'll cause it to become, it'll be transferred to the second subunit, and that will become R as well. So in the sequential model, the subunits change their activity or the conformational shape one subunit at a time in a sequence. One, two, three, four. So hemoglobin has four subunits, for example. So you have, something binding to causing one changing and second changing and third and fourth. That's called sequential. In the concerted model, all four of them will change at the same time. That is the difference between sequential versus the concerted model. Okay, and this is again explained very nicely. It is um, so binding of substrate to one subunit induces the conformational change in other subunits, and so this is bound, this changes, and this causes this to change, and then eventually you have both of them changed in the R conformation. Okay. So again, this is a repeat slide, what we just talked about earlier. And just to refresh your memory, what is the lock and key model as versus the induced fit model? And we've seen this before. In the lock and key model, the substrate and the enzyme are completely complementary to each other, um, and there's no conformational change. It just fits in like a key to a lock. In the induced fit model, uh, there is some sort of a binding site. So there's a binding pocket where things bind to it, and then the conformational changes and makes it completely tight binding. And that's called the induced fit model, um, as opposed to the lock and key model. So make sure you guys understand this simple difference, and you can explain that if needed. This is just another example of the same thing showing lock and key. So in summary, we said there are two models to explain cooperativity. One is called the concerted model, and the concerted means everything happens at the same time. So you have T and R, and this transition from T to R happens, all the subunits changes their shape or conformation exactly at the same time. All four of them have the same thing. That's called the concerted model, and the concerted means together or same time, right? Uh, the other model, which is called the sequential model, in the sequential model, the conformation changes in a sequence. So substrate binds to one subunit, one changes, then two changes, then three changes, and then four changes, right? And that is the biggest difference, and also the way um, the sequential explains cooperativity better, and induced fit model is here. Okay, again, showing you the homotropic versus heterotropic regulation, and then the concerted uh, and the sequential models here. Okay. Now, in summary, again, just to summarize, this is taken from the book as well. The the concerted model, um, concerted means things happening at the same time. Uh, so the subunits, all subunits, exist in the same conformation, whether T or the L. Um, and in the sequential model, the all the subunits do not have the same conformation. It happens one at a time, and it's induced fit model, and it explains the uh, the cooperativity much better than the other model. Um, and you have seen this hemoglobin binding to oxygen binding to hemoglobin, and this is really taken as a classical example of sigmoidal curve binding or cooperative behavior or allosteric behavior. So we know that hemoglobin is a tetramer. It has four subunits, uh, 2 alpha and 2 beta, and each of them can bind oxygen, right? So, and it was shown here, if one subunit binds oxygen, it causes a change in the second subunit here, um, which will bind oxygen more tightly, and that's why it goes up very fast. And then this causes the third, we start changing the conformation, which will bind to the third one, as shown here, and eventually all of them gets saturated. So you have totally unsaturated here, 0% oxygen, and here you have 100% oxygen, and that shows you the sigmoidal behavior, where it you have this part where cooperativity is shown very nicely. Okay, and this in fact, we talk about this, why hemoglobin has that behavior, sigmoidal behavior is such a good thing. And again, please read this. This was in our you know um, uh, this is important, and we want you to understand the significance of sigmoidal binding for hemoglobin, and we discussed this in the class quite a bit as well, the difference between myoglobin, which does not have cooperativity or does not show sigmoidal behavior, versus hemoglobin, which does. Okay. Um, Now this YouTube video, which I'm providing the link here, is really an excellent video. I really like this guy and the way he explains the concerted model and the sequential model for hemoglobin. So as I said, um, some proteins seem to be, there are two models, right? So it's not right or wrong. Uh, One could use one of or the other model to explain the behavior. So what this guy is saying, that if you look at hemoglobin and how hemoglobin would behave if it was following the concerted model versus how hemoglobin would behave if it follows the sequential model. And he explains it very nicely that most likely hemoglobin behaves as if it has a sequential model. And then you'll see it very nicely. So please watch this video. It's very interesting. Okay. I've already talked about feedback inhibition and how allosteric regulation uses feedback inhibition. Sorry, feedback inhibition uses allosteric regulation. And again, in feedback inhibition, a product which is made late in a series of reactions. So like this is a series of reactions shown here, and this is a precursor, this is the final product. And the final product can serve as an allosteric regulation of an enzyme which is um, uh, earlier in the series of reactions, right? So enzyme number one is inhibited, and we talk about this. There's a nice flash animation. Please take a look at it, and again, we explained this quite a bit, so I'm not going to go over this now. But please take a look at it in the book as well. Okay, and this is again ATCS. We talked about that. Okay, so this is the end of part two, and I'll continue with this, inshallah, in part three video. Okay.